So today we will see how to solve another optimization problem using dynamic programming. The problem which we will take today is called the polygon triangulation. So in polygon triangulation, first let me tell you what do we mean by a polygon. You must have already an intuitive idea of a polygon. So it's a set of vertices and edges such that it bounds a region in a plane, roughly speaking. So this is the definition of a polygon. So here I am drawing one polygon. You can see here is a polygon. So most of the time our convention will be to traverse the polygon in a counterclockwise manner. So this is the direction of our traversing this polygon. So when we give this set of edges with vertices, it has a distinct sense of what is interior. So this is the interior of this polygon and this is the exterior of the polygon. And we call this one as the boundary, which consists of edges and vertices. Now a polygon can be a convex, like here I am drawing a convex polygon. So here is a convex polygon. The one here which I have drawn previously, this is a non-convex polygon. So this is a non-convex polygon, this is a convex polygon. The definition of convexity is basically if you take any 2 points in the interior and if you join the 2 points with a line segment, that entire line segment should lie within the polygon. Then it is called the convex, if it happens for any 2 points in the interior of the polygon. Like here, if I take this point and this point, in this case this line segment does not lie totally inside the polygon. So this is a non-convex polygon, but this case will not happen in this figure. So this is a convex polygon. Now the triangulation algorithm, what we will look into, actually in the book it has been given to work on convex polygons only, but we will see that we can easily make it to work also on the non-convex polygon, and we will do it because this is more general case. So this is the notion of what is a convex non-convex polygon. Now what do we mean by a triangulation of a polygon? Triangulation of a polygon means, so let me draw this one more polygon. So I have just drawn an arbitrary polygon here. A triangulation of this polygon means we will dissect or decompose the interior of this non-convex polygon into triangles. Okay, such that the vertices of the triangles come only from the vertices of the given polygon. You are not allowed to have extra vertices. So if we do this, so I am just drawing one triangulation, you can see that. So here this figure, so this is one triangulation of this polygon. You can see that interior of the polygon, each one is a triangle now. It has been decomposed into triangles, and all the vertices of the triangles are coming from the vertices of the polygon. So this is the triangulation. Now the question is, the first question is it always possible that a polygon can be triangulate all the time? That's the first question which comes into mind, right? So given any arbitrary polygon, what is the guarantee that you should be able to draw such edges such that the interior of the polygons is broken up into triangles? So is the question of feasibility, is it at all feasible to do it? And the answer to this question is yes. It is always possible that you can triangulate a given polygon, no matter how it is given. Again, I repeat, the polygon edges do not intersect among themselves. So it's a clear boundary which bounds a clear interior. So they do not intersect themselves. There is no self intersection. So what is the proof? So here is a claim, first claim. The claim is every polygon is triangulable. So let us see why it is so. The proof for this one goes by induction. First of all, we will be inducting on, so this is by induction on the number of vertices. Induction on number of vertices. Do I have to say anything about the base case? So if the number of vertices is 3, it's a triangle and there is nothing to triangulate. So it's all definitely triangulable. So base case is very easy. So base case is triangle, no problem. Now for the inductive step, what do we do? You consider the leftmost point of the given polygon. So let me just draw one, it's an abstract polygon, okay, in the sense that I did not draw all the edges very carefully. So this is the boundary of a polygon, and take the leftmost edge here. Sorry, not leftmost edge, leftmost vertex. So let us call it as P. Now this leftmost vertex P has one edge which is coming into it if we traverse the edges in the counterclockwise manner, and another edge which is going out of it. So let us call it as A and B, these two vertices. Now there are two cases. Case 1, AB is a chord. What do you mean by chord? Chord means the segment AB does not intersect the boundary of the given polygon. Okay. So if I draw this edge AB, AB does not intersect the given boundary. So in this case, you can go on inducting on what? On the rest of the polygon. So you take out PAB as the triangle and you carry out your induction on the rest of the polygon, which is nothing but AB and rest of the boundary. So you carry out your induction on this part now. Now certainly this polygon has how many vertices? One less. If the original polygon had n vertices, this one has n minus 1 vertices, and I can carry on the induction on it. So this case is true. You take out the triangle PAB, and by induction the rest of the polygon is triangulable because we are inducting on the number of vertices. What is case 2? Let me draw it another picture. So here is the case 2. Case 2 is this, that there is a leftmost vertex P, but the polygon itself comes inside the chord AB. So if I try to draw the chord AB, it intersects the boundary. So in this case, I cannot say anymore that PAB is a triangle, take it out and triangulate it the rest, because that's not valid now. Because PAB is a triangle, but it is intersecting the boundary itself. You cannot take it out. So in this case, what you do, since the boundary is intersecting the segment AB, on that boundary there must be a vertex, say V, which is leftmost. Like here, what I have just drawn. There is a vertex V. And you join P and V with a chord. And I'm sure that P and this segment cannot be intersected by the boundary. Because if it does, then there will be another vertex which is nearer to P than V. But we have chosen V such that it is the nearest to P. So you draw PV. So you draw PV, and then you carry out the induction on this N1 gone, say this one N1 gone, and this is say N2 gone. You have two polygons now. There is one part is here, there is another part here. Now on these two polygons you carry out your induction because they have at least one vertex less. So by induction, this is triangulable, this is triangulable. Take the two triangulation and add the chord PV. It's a trivial fact now. Once you get this triangulation and this triangulation, you have got the triangulation of the entire thing. Almost straightforward. Okay. So this says carry out the induction on two subpolygons. So basically N1 plus N2 is equal to what? Can somebody tell me this? No, it is N plus 2 because these two vertices are counted twice. So this is N plus 2. Okay, and we also know that N1 and N2 both are less than N strictly. So you can for this one I can carry out the induction on these two subpolygons. So this proof now says that every polygon given as we said that if it is non self intersecting, then we can always triangulate the polygon. Now let us go back to one triangulation which I drew here. So let us go back to this figure. You can see the triangulation which I drew is very arbitrary. I just started drawing some edges. Like I can tell you, instead of taking this edge, I could have taken also this edge. If I take this edge, this triangulation is different from the previous one. So you delete this edge and insert this one. I may take this, I may delete this one, insert this edge. So there is no unique way of triangulating the polygon. So there may be several ways of triangulating a polygon. Now the question is, how many such different triangulations are possible? It can be proved that given a polygon of n vertices, in the worst case there are exponentially many different triangulations, something like 2 to the power some n, 2 to the power some constant time n. That many triangulation are possible in the worst case for a given polygon. So among all these different triangulations, the question is asked in optimization is that find out a triangulation which optimize some criteria. So let us take one of the criteria as the length of the edges of a triangle. So take the length of the edges, sum the length of the edges of the triangle, and that put that one as the weight of the triangle. So given a triangulation, each triangle has a weight. What is the weight? Weight is the basically the perimeter. So once you take that weight as the the perimeter as the weight, I can ask what is the weight of the total triangulation. The total weight of the triangulation will be nothing but the sum of all the perimeters. So that is the weight of the triangulation. So given a triangulation, we have a weight of the triangulation. Now I can ask, among all possible triangulations, find out that triangulation which minimizes the total weight. So precisely you are asked now, find out that triangulation where sum of the all edge lengths is the minimum, when some of the internal edges are counted twice, because it will be counted once for each of the triangle incident on it. Okay. So that is the problem. So given this problem, how can we solve this optimized triangulation problem? We will see this can be quite easily solved using the dynamic programming. We will see that how to use dynamic programming in this particular case. Now before I go into the detail of the algorithm, let me just use some of the terms or tools which I will be using in the algorithm, which is called the left turns. What is the left turn? Suppose I have 3 vertices A, B, C, and I know I am traversing them in a counterclockwise manner. So A, B, C, and suppose A is AX and AY are its X and Y coordinate. Similarly, B is BX, BY, C is CX, CY. So these are the X and Y coordinates of these 3 points. So first thing is a polygon. This is just a fact I want to state. A polygon is convex if and only if any 3 consecutive points or vertices form a left turn. So for a convex polygon, let us see here. For a convex polygon here, if you take any 3, these 3, they form a left turn. Take these 3, they form a left turn. Take these 3, they form a left turn. Any 3 consecutive ones will form a left turn. Not only it is true that given a convex polygon it is true, if this is true, the polygon is also convex. It's an if and only if condition. It's true in both directions. But suddenly you will see this will be invalid for non-convex polygon. Like if you take this 3 consecutive ones, it is not making a left turn, it's making a right turn here. So this is not a convex polygon. Now, given this fact, left turns, how can we decide from the coordinates of the 3 points A, B, C whether they will make a left turn or not? So there is a very easy formula. The formula is this. Here is a claim. I will not prove this claim, I leave it to you, but it should be quite easy. If you manipulate this formula algebraically, you will find why it is. Why is it true? So we say A, B, C, the 3 points make a left turn if and only if, again, if you calculate this determinant Ax, Ay 1, Bx, By 1, Cx, Cy 1. If you calculate this determinant and if its value is greater than 0, basically its sign is positive, then this will make ABC will make a left turn in the counterclockwise manner. And if it is less than 0, it will make a right turn. It is an if and only if condition. And actually if it is 0, that means these 3 points are collinear. And we will not consider that case. We will assume that no 3 points are collinear. Alright. So suppose somebody asks you to verify, given a set of points, whether they are making a convex polygon or concave polygon or non-convex polygon, you can checking this determinant for every 3 consecutive points, you can decide that one. Need to compute this determinant. Now I just assume, now I am going into the details of the algorithm very slowly. I am assuming this input. The input for the polygon has been given as a set of points. So points in a C type language will be a structure basically, and that structure will have 2 fields, x field, x coordinate and y coordinate, and I will have an array, say P. The array P will be nothing but, say it goes from say 0 to n, and Pi basically points to the vertex I. Okay, so basically it will be pointing to a structure, and that structure will contain the coordinates of the vertex I, x and y. So that's the data structure I am assuming, that's the input for the polygon. And the vertices are given in the order of the counterclockwise traversal of the boundary. So if I go over P0, P1, P2 up to Pn, I will be traversing the polygon in a counterclockwise manner. So now let us see how can we do the dynamic programming here. Let me draw some arbitrary boundary polygon here. So this is a polygon, suppose. I am just drawing with curved edges, but basically they are straight line edges. You take a point vertex say I, and we are trying to say, don't take I there, I take I here and I plus L here. Suppose instead of concentrating on triangulating this entire polygon in an optimized version, we concentrate only on triangulating the portion between I and I plus L. So I and I plus L. So this polygon, we try to triangulate I and I plus L between that these 2 indices, whatever polygon part is lying, that sub polygon, we want to triangulate this one in the optimized fashion. So what will you do? Suppose you want to do that. Any triangulation, any optimal triangulation for this sub polygon must have a triangle which will be incident on this edge I and I plus L, right? One triangle at least will be incident on this edge. So let the triangle be somewhere here, say this is in I plus k for some value of k. So I am looking at the optimal triangulation of this sub polygon, and suppose this one has this triangle. So there is a triangle I plus k and I plus L. So this triangle is present in the optimal triangulation of this sub polygon. Now definitely if this entire triangulation of this sub polygon must contain a optimal triangulation of this part. another subpolygon and must contain another optimal triangulation of this subpolygon. Otherwise, the optimal triangulation cannot be a optimal triangulation for the whole thing, the entire thing here. Suppose you are considering the optimal triangulation of this polygon I to I plus L, then there must be one triangle for some value of I plus K, for some value of K, such that this subpolygon, that is between I plus K and I plus L, and there is another subpolygon I to I plus K, both the subpolygons must be optimally triangulated. Otherwise, your entire triangulation cannot be a optimal triangulation for this subpolygon. Have you understood this? This is a very crucial thing to understand for your dynamic programming approach. Yes. So let me take this one separately. Suppose this is a polygon. I have just taken one polygon here, right? So suppose this is an edge A and B. So there is one optimal triangulation. You understand what is the optimal triangulation? I just told you optimal triangulation is the triangulation which minimizes the total weight, and weight you can take as perimeters, as I told you, sum of the perimeters of all the triangles. Okay, now there is one optimal triangulation. Consider that optimal triangulation. Let us call that one as T star. Now that optimal triangulation must have one triangle which is incident on AB. Is it true or not? It must be there. Okay, let me draw that one. I don't know where it is, but there exists one. Okay, let's say that it is happening at place say C. So this triangle is present in the optimal triangulation. Now that triangulation T star must have a triangulation of AC and this part, and also a triangulation of this part. Now what I am claiming, the triangulation of AC, this part, must be also optimal. Otherwise you could have taken another triangulation of this part which will be better, but you already took T star to be the optimal triangulation. Can you follow what I am saying now? The triangulation given on the part AC and this curved portion, which is imposed by T star, must be also optimal for this polygon. That's my claim. Is it clear? Is it clear to everybody or not? Because the claim is very straightforward, because suppose it were not, that means you are claiming that this part has a better triangulation, then take that better triangulation, then add it to the rest of the triangulation which will be a better triangulation than T star, but you have already taken T star to be the optimal for the original one. There cannot be anything better than T star. So that's the claim I am making here now. Take the subpolygon between I and I plus L for some value of L. Then we are looking into that optimal triangulation of the subpolygon between I and I plus L. The claim is just what I just said here. There must exist a value of K such that I plus L, I and I plus K is a triangle in the optimal triangulation, and these two subpolygons must have optimal triangulation given by the optimal triangulation of the original. And that gives you the foundation of how to use dynamic programming here. What can we do now? Suppose we have found out all the optimal triangulation of this I plus K and I plus L between any I plus K and I plus L for different values of K. Suppose. Then you take all possible values of K and check the total weight of the triangulation which you are getting, and take the one which is the least. So carry your K now. So you can, since you don't know which one is optimal, we are going to check for all possible values of K. I know this edge is there, suppose, because this is a part of the subpolygon. I choose K first here. Once I choose K, I plus K here, I have this subpolygon and there is a teeny little subpolygon here. I have already computed these two optimal triangulation of these subpolygons. take these two subpolygons, add the weight of this triangle, that becomes the weight of this triangulation when you assume that I plus k is the one which is making a triangle with I and I plus l. Now you vary your k over this entire boundary. At some point you will be getting the correct one, you are assured of that, because your optimal one at least have somewhere the connection between I plus l and I plus k for some value of k. So you vary your k on this boundary and check the total weight of the triangulation, whichever gives you the least, you are sure that that is the optimal one. And where is the dynamic programming? Dynamic programming is where you keep this optimal triangulation, the value of the optimal triangulation of this part in a table, just like what we did in the matrix chain multiplication. We kept the sub problems, the value of the sub problems in a table, in a 2 by 2 matrix. That is what we will do here also. All the lower sub problems, the value of the lower sub problems, we will keep the value in a table. So did you follow what I am just trying to say? Because once you have followed it, if I write the algorithm, it will be almost immediate. So let me just repeat once more using another picture. So here I am drawing a bigger polygon so that I can make mesh over a larger portion of the paper. So here is I and I plus L. Okay, I am interested in finding the optimal triangulation of this part. Now I take first say this as k, so I take this say I plus k, and in the algorithm will be such that this subpolygon triangulation, the optimal triangulation of this subpolygon is already made and has been kept in a table. I take the value of this optimal triangulation, I take the value of this optimal triangulation, add the weight of this triangle, that gives the weight of this triangulation if I make the choice of k as this vertex. Now you vary your k, now your k becomes this. Now your subpolygons has changed. Now your subpolygon is this part, your subpolygon is this part. Take this triangle, add this weight and check whether this is less than the so far you have computed. Vary your k, again go on doing this and keep the one which is the minimum among all this, and that will be the value of the optimal triangulation for this subpolygon now.
So suppose we have a case such that the line joining I plus L and I plus K fall outside.
Right. That's a very good. What he is saying is that suppose we have a case I and I plus L, that line intersect the boundary. Then definitely we cannot take that one as the chord, or we cannot consider that as a subpolygon. And in the algorithm we will see how can we take care of it, and that's why this left turn business come into picture. We will check whether, if now here you can see I plus L, I and this vertex I plus K must be a left turn. It must be a left turn. It must be a left turn, and this polygon should have a triangulation over this chord. This polygon should have a triangulation over this chord. This is a recursive definition. Then this chord is valid. And this is the check we will make in the algorithm also. So now let me tell you, in the dynamic programming, how would you formulate your dynamic programming? See, most of the cases in the dynamic programming, it will be 3 variables which you have to vary. But before you use these 3 variables, you have to be very clear in your mind how to vary them. So here are the variables. I is 1. Basically I will be varying from 0 to n minus 1 or something like that. Then this L will be varying. First it will be between I plus 2 maybe, I plus 3 maybe, I plus 4. It will be increasing, L will be increasing. Okay, and so that is the second variable. And the third variable is your K. Between I and I plus L, you will be varying the variable K. And that gives you the 3 variables, how you are varying this. Okay, so when I am saying you are keeping the optimal triangulation of the subpolygons in a table, What does it mean? It means since you have varied L from say 1 to say it's increasing. So you have already computed all the subpolygons which are lower than the subpolygon you are considering now. So like what I am saying is when you are considering I and I plus L, you must have already computed between I plus K and I plus L. Because this is much smaller than this entire. So not only 3 variables you have to vary, but you need to know how to vary them, in which order properly. If you have this picture in your mind clear, then only you can write the algorithm. The dynamic programming algorithm will be very short. It will be only 3 loops. But use of the variables is not so straightforward if you don't understand it properly. It's very structured, the algorithm. So let me just now tell you the algorithm. So I will be using 2 matrices again to keep the as a table, the dynamic programming table. I need to use some table. So one is T, which goes from 0 to n minus 1 and 1 to n minus 1. And there will be another table V 0 to n minus 1, 1 to n minus 1. Okay, what does it do? TIL stores the weight